Hello class and welcome. Today we're going to be talking about the conservation of mechanical energy again as a review. Well, first of all, let's consider this roller coaster. It's a very simple wooden roller coaster. It starts up high after the first big lift hill, and then it goes down to point C, comes back up to point D, and then it goes back down again to point E. So it's got one main hill at point A, and it's got a little hill here at point D. Let's consider how the energy is changing in this system, and we're going to make one big assumption. We're going to assume, we're going to assume that the non-conservative work done here is zero. So basically there's no friction, okay? There's nothing like that going on here. The total mechanical energy is going to stay the same. In order to analyze this problem, I've constructed an energy bar diagram at the bottom. Let's go through it step by step. Look at point A. This roller coaster car is not moving at all. It's at the top of the hill. Its total potential energy, in fact, all of its mechanical energy is stored potential energy right here. You can see this entire bar is filled with U, potential energy. Kinetic energy down here is zero. But then, as a roller coaster moves down to point B here, it's decreased in height. So it's lost some height, which means automatically it's lost some gravitational potential energy. And you can see in this energy bar diagram, I've drawn that U is a little bit shorter. And where'd the energy go? Well, it went to kinetic energy. If you were to take this and put it up here on top of here, it would be the exact same level that we started out with. That's because we've made the assumption that your non-conservative work is zero. And then at the bottom of that first big hill, look, the potential energy is zero, and your kinetic energy is now equal to your total mechanical energy. In other words, all the energy has been switched over from potential energy here at point A to kinetic energy here at point C. I want to make an important point here. How do I know my potential energy here is zero? After all, this is not at ground level. It's not even at sea level. Because I can choose my reference height to be whatever I want. So here I've chosen for point C and point E to be the bottom where height is equal to zero. By definition, this is a point where your potential gravitational energy is equal to zero. Now look, the car goes up again to point D, you know it's going to slow down. And in fact, that's exactly what happens. Look, it's gaining potential energy again, and it's losing kinetic energy, okay? They've swapped back temporarily. Because look, at point E, again, all the potential energy has been lost, and we have kinetic energy again. So, an energy bar diagram is a very good tool for conceptualizing what's going on with the energies here. It's going from potential to kinetic, and then it switches back again temporarily, and then it goes back to all to kinetic again. By the way, what if we were to extend this roller coaster? What if we were to extend it like this? So that the hill went up, and we had a third hill. Well, we know automatically that this hill has a height limit, because that hill cannot come any higher than point A. Once a roller coaster reaches this point on this hill, it will stop and turn back around. All right, if there's other cars coming, that'll be a big issue. So that's why on old-fashioned wooden roller coasters, and even modern steel roller coasters that rely on lift hills, the first hill is always the highest point. All right, let's move on. Okay, we're going to be looking at a very simple sort of situation with a skier. Here's the skier. I don't know what he's skiing on because it's February and today was 80 degrees, but let's say he's going down the hill anyway. He starts at point A with no kinetic energy. He's not moving at all. And you can see this represented down here in the potential energy diagram. And then as he skis down the hill, well, you know he's going to pick up speed. He has an acceleration down the hill. And then down here at point C, all of his energy has been turned to kinetic energy. So as time progresses, your potential energy goes down and your kinetic energy goes up. So you're losing stored energy and you're gaining speed energy. Again, we're making an assumption here that the non-conservative work done on the skier is going to be 0. That means there's no friction between him and what would apparently be a grassy hill, since there hasn't been snow in a while. We can actually improve this bar diagram by drawing a little line here. So imagine points between A and B, and between B and C. What would the potential energy look like? Well, I can connect these dots, and you can see it would smoothly go down. And what would kinetic energy be doing? Just the opposite. All right, it's smoothly going up. And of course, there's a point somewhere in the middle, which is going to be exactly halfway down this hill, where your kinetic energy and your potential energy are going to be equal to each other. Okay, so let's talk for a second about the problem-solving strategy with these energy problems. All right, so your first step is to very carefully identify the system. What's inside the system, what's outside the system, okay? Now, let's be a little more specific here than we've been. In a skiing problem like this, a simple problem like this, the skier himself is actually not your entire system. The system would consist of the skier plus the whole Earth itself. Because remember, the gravitational potential energy is stored between two objects that are gravitationally attracted to each other. So we wouldn't say it's the skier's potential energy. We would say it's the skier, let me write this down, it would be the skier Earth system, which is storing that gravitational potential energy, okay? If you want to think about it like this, the skier is here, all right, this is not to scale, and the Earth is here, and there's a gravitational attraction between them. It's a little bit like a spring. The higher up the skier goes, the more energy is stored, okay? And the farther down the skier goes, the more energy is released. But generally speaking, that's a technicality. Okay, your next step is going to be this. Identify the forms of energy. Which forms of energy are part of the total mechanical energy? Okay? Well, generally speaking, if you have some sort of potential energy, that has to be a part of mechanical energy. And obviously kinetic energy is going to be part of mechanical energy. But if you have other forms, say you're losing energy to heat through friction or something like that, you have to consider how your total mechanical energy is being formed. Okay? Step 3 is going to be to identify the initial and final states of your system. Okay? Where is your initial point and where is your final point? This whole idea is comparing the initial and final states and comparing the initial and final energies, whether it's total energy, potential energy, or kinetic energy. All right, now step 4. You have to figure out if energy is being added or removed from the system. If it's not, then your total mechanical energy is conserved, and we can say the final energy is equal to your initial total mechanical energy. Okay? Both these examples we looked at just now with the roller coaster and the skier, these are both systems where your non-conservative work done is equal to 0. We were assuming that there was no friction. We were assuming that, for example, the skier didn't have some sort of rocket pack or something like that. The work done by the non-conservative work done on the system would be 0 here. But what if some energy is added, or even some energy is removed? Then your final mechanical energy is whatever you had initially plus the energy added to the system. Now remember, your non-conservative work is equal to your change in total energy. So this actually makes a lot of sense. If we're losing 500 joules through friction, then your final total energy is going to be 500 joules less than your initial total energy. If we're adding 800 joules, because someone's pushing on the roller coaster from behind, then your final total energy is going to be 800 joules more than your initial. Again, the energy parts of these problems, where you're actually dealing with the energy, it's simple addition and subtraction. Okay? And in fact, look, if no energy is added or removed, we can expand the definition of total mechanical energy, and we get this. Initial kinetic energy plus initial potential energy is equal to final kinetic energy plus your final potential energy. And if energy is being added or removed, we get this. So your last step is going to be to evaluate either of these two equations to solve what it's asking for. Now, just a reminder, this can be positive or it can be negative. So keep that in mind. All right, we're now going to be looking at an example problem. I believe 2 videos ago I told you to think about this. What if you had a system that involved both spring potential energy and gravitational potential energy? All right, a system like that would happen if you had like a block that's being moved by a spring, which is also moving vertically. In that case, the movement of the block vertically will be changing its potential energy, it'd be changing its gravitational potential energy, but it'd also be changing its spring potential energy because the spring is doing conservative work on the system. All right, so here's a problem. We've got some generic physics block on a compressed spring, and then the spring is released, and the spring rushes upward, it's pushing the block along until it reaches its equilibrium height. We don't really care about what happens afterwards. I would assume the block would continue upwards and kind of fly up a certain height, but we don't really care about that. Our question is this: how fast will this block be going when the spring reaches that equilibrium point? All right, and we're going to be able to solve this using conservation of energy. Well, let's see. What sorts of energy do we have here? We have the stored spring energy. We're also moving vertically, so we have some sort of stored gravitational energy. And then we have a velocity change. So we're also dealing with kinetic energy. You know what I don't see here? I don't really see any reason to include any friction or drag. The problem doesn't state anything about friction or drag, and there's no coefficient of friction or anything. So I think we're very safe to make the assumption that for the purposes of this problem, the non-conservative work is so low that it's going to be essentially zero. So no outside energy is added to or removed from the system. Okay, well, what's the system here? The system is going to consist of 3 things. This block, the Earth itself that's attracting the block, and this spring here. So the Earth and the block system can store gravitational potential energy, and the spring itself can store spring potential energy. All right, we've got some numbers here. The mass of the block is 2 kilograms. The distance or displacement of the spring from its equilibrium position is 4.6 centimeters. And the K constant for the spring is 955 newtons per meter. Remember, the K is a stiffness measurement for the spring. If this number is higher, you have a stiffer spring which can store more energy. Okay, to solve this problem, it's going to be pretty straightforward actually. So we know, since our non-conservative work is zero, that our initial total energy is equal to our final total energy. All right? So let's examine, first of all, our initial total energy. Well, that's just our initial potential energy plus our initial kinetic energy. Now, let's look at what these terms actually are. These first 2 together, that's going to be our initial potential energy. And this here, this 0, well, you guys probably already know this. This is your initial kinetic energy. Remember, the block is not moving before the spring is released. It's just resting there. Kind of like a jack-in-the-box. Okay, well, let's examine this because this is something we've actually never seen before. We have 2 different types of energy contributing to potential energy. This is your gravitational potential energy, and this is your spring potential energy. Now, the spring potential energy should make a lot of sense to you guys. 1/2 kd squared. Well, what's d? D is the displacement of the spring from equilibrium. Now, we've seen this before as 1/2 kx squared. Since we have a vertical motion here, x doesn't really apply, so you would just switch out the d for the x. Hopefully that makes a lot of sense. Now, here's the trick here. What about this potential energy? Why is this negative? How can we have a negative gravitational potential energy? Well, remember what I've been saying. You can set your zero height, your reference height, to be whatever you want. It's actually arbitrary as to where you set your h is equal to 0 point. And look here. For our convenience for the spring potential energy, we've set the point where, we set the final condition where the block is finally, we've set that height as y is equal to 0. So initially, the block was actually at a negative position. Y is equal to negative d. So it's going to be negative 4.6 centimeters. Okay? If you're below the reference height, it doesn't actually pose a problem for gravitational potential energy. It is okay for that to be negative. So this is actually perfectly okay. So let's move on. All right, so what's our final total energy? Well, it's going to be our final potential energy plus our final kinetic energy. Now we know, since the block is at a height of 0, that your final gravitational potential energy is actually 0, mgh. And we know, since the spring is at equilibrium, there's no displacement of the spring. So your spring potential energy is going to be 0. And then, of course, you guys recognize this. This is your kinetic energy. Let's make sure this looks like a capital K. There we go. This is going to be your K final. Okay, solving for this problem is pretty straightforward. Excuse me. So let's go back here. So we know that your initial energy is equal to your final total energy. So we know that ui plus ki is equal to uf plus kf. And we know that our initial kinetic energy is 0. And we know that our final potential energy is 0. So we have a very simple relationship here that we're going to take advantage of. Your initial potential energy is equal to your final kinetic energy. This is definitely not true for every single type of problem we have, but for this problem it is. That's because our initial kinetic energy was 0 and our final potential energy just happened to be 0. Okay, so we're going to set ui is equal to kf. Now all we have to do is find our initial potential energy and we can find our final kinetic energy. So we're going to set this up. We're going to plug in some numbers. 2 is your mass, 9.8 is little g, and 0.046, that's going to be your displacement in meters. So we had to convert those centimeters into meters. Remember, we're not measuring energy in arbitrary terms here. We have to get them in joules. That means our mass has to be in kilograms, that means g has to be in meters per second squared, and that means any distances or heights has to be in meters. All right, and there's our k constant here. And again, this is d squared. Don't forget the squared in meters. As we expected, our gravitational potential energy is going to be negative. But the spring potential energy has a higher magnitude. That means your overall potential energy is going to be positive. Now, this had to work out this way, or the problem wouldn't have been justifiable. If your initial potential energy was negative, then we could not have a final kinetic energy that was positive. Okay? So we know our final kinetic energy is equal to our initial potential energy. So we know V is equal to 0.32 meters per second squared. Now, how did I get this? I just used the kinetic energy equation. If you were to rewrite this equation to solve for V, you would get something like this. K is kinetic energy, 2 is 2, and m is your mass. And this is the square root of this entire fraction. Now, on your AP test, you're definitely going to see some problems like this. Solve for V in terms of K, D, M, and G. What this means is that we're going to have to solve for velocity in terms of your spring constant, the distance of compression, the mass of the block, and G. This is going to require manipulating the equation in terms of these variables. And our end result is just going to have variables in it. It's not going to have numbers. Now this here, this is pretty easy to digest. At any point in the calculation, we know what the individual terms mean. I can go down here and I can say, oh, well, the negative 0.9016, that's your initial gravitational potential energy, okay? So it's easy for your brain to kind of follow along with this. But it's not always going to be true when you're solving for V or when solving for a variable in terms of other variables. It's easy to get confused. So we're going to walk through this together. Okay, from my initial setup conditions, I've got this. Negative mgd plus 1/2 kd squared is equal to 1/2 mv squared. Remember, this is your UG, this is your U spring, and this is your K final. Then we have to solve this in terms of V. What this means is we have to get V by itself. So our first step is going to be this. We're going to be multiplying both sides of the equation by 2. A lot of students really want to divide both sides, by 1/2. But that's going to confuse you. The best way to do this is just to multiply both sides by 2. So we get negative 2 mgd plus, well, 1/2 times 2. I'm distributing the 2. It's just going to be 1 plus kd squared is equal to 2 times 1/2, which is what we wanted to do, mv squared. Now our next step is going to be to divide all sides by m. Again, we're trying to get v by itself, so we're moving progressively in to the equation. In this first term, the m's cancel out. No luck here. And of course, in the mv squared term, the m's cancel out. Okay. So I have negative 2gd plus kd squared over m is equal to v squared. So you know how I said the other way to do this problem made a lot of sense? Because we could tell what the terms were individually. What is negative 2gd? Like physically speaking, what is it? I don't know. I have no idea. What is v squared by itself? I mean, does that have any physical meaning? I have no idea. What's kd squared over m? Can't really help you there. And you guys should see pretty easily the last part's going to be this. So I'm going to flip over to this side. So I have v is equal to, just going to square root both sides of the equation. And I'll rearrange these. Why not? This will be kd squared over m minus 2gd. So we've kind of written the equation of this problem. This is not going to apply to pretty much any other problem. It's just the equation for velocity in this particular problem. Okay? Now the good news is we could easily now plug in the numbers and get v as an actual number. So this is what, 955 times 0.046 over the mass, which is 2. And 0.046. You know what? We'd be in a lot of trouble if this term here was bigger than this term here, right? Because then we'd have a square root of a negative number. This actually goes back to the idea that in order to get to that original height, if your gravitational potential energy is too high, it's really not going to work. Okay, solving that out, and we get v is equal to 0.32 meters per second. Okay, so there definitely are certain problems where they would actually want this as your answer. And that's when they ask you to solve for a certain variable in terms of other variables. But there is another motivation for this. It's actually very easy to plug in different values and see what we get. Well, let's say the block was 3 kilograms instead of 2. We could find out the velocity very easily by just switching out a 3 for a 2 here. Okay? It's going to make comparing different values a lot easier. We'd have to redo the entire other problem. But here we can just plug a number into a formula and just plug and chug. Okay, so that's it for today. Thank you for watching.